I know you're afraid. Afraid of math. Afraid of matrices. I came here to tell you it's not that hard. I'm going to show you the rules and controls and boundaries. I'm going to show you can do it too. Where you go from there is a choice I leave to you. In this video, we're going to learn what a matrix is, how to add and subtract matrices, how to multiply matrices, how to manipulate a matrix, how to use matrices to solve systems of trivariate linear equations, and determinants and Cramer's rule. So, what is a matrix?
Do you want to know what it is?
A matrix is a substance, situation, or environment in which something has its origin, takes form, or is enclosed. In mathematics, it's a rectangular array of elements set out in rows and columns used to facilitate the solution of problems, such as transformation of coordinates. So a matrix is an array of mathematical elements used to arrange and solve systems of equations, written between vertical lines or square brackets, arranged in rows and columns, ordered as row by column, and elements are written as A sub row, comma, column in a general matrix. The rules for adding and subtracting matrices are as follows. Rule number 1, the matrices have to have the same order. Rule number 2, that's it. Here we have two examples, matrix A and matrix B. Both have an order of 2 by 1, which means A plus B, A minus B, and B minus A are all valid operations. To add or subtract matrices, simply combine like elements. For example, the element in row 1 column 1 of matrix A plus the element in row 1 column 1 of matrix B will give you the new element in row 1 column 1 of our new matrix C. Same thing for A minus B, row 1 column 1 minus row 1 column 1 gives you row 1 column 1. So for example, if we're going to add matrix A plus matrix B, we're going to get negative 5 plus 15 for row 1 column 1 and 22 plus 3 for row 2 column 1. For B minus A, we're going to get 15 minus negative 5 for row 1 column 1 and 3 minus 22 for row 2 column 1. So now we have two new matrices here, matrix A and matrix B. We're going to treat the x variables like constants, and we're going to solve A plus B, A minus B, and B minus A. So first we're going to do A plus B, and I'll give you a few seconds here to try and work it out yourself. Okay, so now we've had some time to work on it, and we're going to do it here together. We have x squared plus negative 2x squared. That's going to leave us with negative x squared in row 1, column 1. We're going to get 23x plus negative 3x, which gives us 20x. Next we get 5 plus 20, which gives us 25. Now for row 2, column 1, we get negative 4x squared plus x squared, which gives us negative 3x squared. For row 2, column 2, we get 4x plus x, and that's 5x. And last we get 2 plus 0. So 2. Now take a few seconds to work on A minus B. Okay, so for a minus b, we're going to get x squared minus negative 2x squared for row 1, column 1, and that's 3x squared. 23x minus negative 3x is 26x, and 5 minus 20 is negative 15. Negative 4x squared minus x squared is negative 5x squared. 4x minus x is 3x, and 2 minus 0 is 2. So we have a minus b gives us 3x squared, 26x, negative 15, negative 5x squared, 3x, and 2 for our new matrix. And take some time to do b minus a. So we're going to get negative 2x squared minus x squared, so negative 3x squared. Negative 3x minus 23x, and that's negative 26x. 20 minus 5 is 15. X squared minus negative 4x squared, and that's 5x squared. X minus 4x, so negative 3x. And 0 minus 2 is negative 2. Now that we've done addition and subtraction, we're going to work on multiplication. Multiplication of matrices is only possible if the columns of matrix A is equal to the rows of matrix B. If the columns of matrix A is equal to the rows of matrix B, then matrix A times matrix B is valid. If the columns of matrix B is equal to the rows of matrix A, then matrix B times matrix A is valid. If the columns of matrix A are equal to the rows of matrix B, but the columns of matrix B are not equal to the rows of matrix A, then matrix A times matrix B is valid, but matrix B times matrix A is not valid. So here we have three matrices. Matrix A has an order of 2 by 1, matrix B has an order of 3 by 2, and matrix C has an order of 1 by 3. So A times C, B times A, and C times B are valid, and A times B, B times C, and C times A are not valid. If you have a valid operation, then the order of the new matrix is going to have the rows of matrix A and the columns of matrix B. We're going to multiply each row from matrix A with each column from matrix B. So row 1, column 1 of our new matrix has 1 times A plus 2 times C, and row 1, column 2 of our new matrix has 1 times B plus 2 times D. And you're going to repeat that with each row. Now we have three new matrices. Each of them has a different order. I'd like you to find the valid operations and the invalid operations. So take a few seconds. Hopefully you had enough time, and we found that the valid operations are A times C and C times B, and the invalid operations are A times B, B times A, B times C, and C times A. Now we're going to solve A times C and C times B. So take a few seconds and see if you can work out A times C. So we're going to get 3 times 3 plus 4 times 0 plus 1 times negative 1. So 9 minus 1. 3 times 1 plus 4 times 0 plus 1 times negative 3, or 3 minus 3. Then we get 0 times 3 plus 9 times 0 plus negative 8 times negative 1, and that's negative 8 times negative 1. Then we get 0 times 1 plus 9 times 0 plus negative 8 times negative 3, so negative 8 times negative 3. 15 times 3 plus negative 1 times 0 plus 2 times negative 1, which is 45 minus 2. And 15 times 1 plus negative 1 times 0 plus 2 times negative 3, which comes out to 15 minus 6. And then we just reduce our answers. So take a minute for C times B. We're going to get 3 times 2 plus 1 times 0. Then we're going to get 3 times 0 plus 1 times negative 2. We get 0 times 2 plus 0 times 0. 0 times 0 plus 0 times negative 2. Negative 1 times 2 plus negative 3 times 0. And negative 1 times 0 plus negative 3 times negative 2. Now we're going to reduce our answers, and we're ready to learn how to manipulate a matrix.
What are you trying to tell me? That I can dodge bullets?
No, Neo. I'm trying to tell you that when you're ready, you won't have to.
There are 3 operations that you can use to manipulate a matrix. All 3 of them involve rows. You can swap rows, you can add rows together, or you can multiply a row by a constant. And those 3 can be used in conjunction with each other. Now we're going to see these operations in action. First, let's designate our rows as R1, R2, and R3. Now we're going to swap row 1 and row 3. And as you can see, it's really that simple. Now we're going to add row 3 to row 2. And because we're adding row 3 to row 2, the solution is written in row 2. Notice that row 3 did not change. Here I'm going to show you 2 separate multiplication operations because one of them is going to serve in place of a division, since we can't divide. We're going to multiply row 1 by 1/3 and multiply row 2 by 2. Now that we've covered how to manipulate a matrix, we're going to look at using matrices to solve systems of trivariate linear equations.
It's impossible.
It's actually not impossible. What you're going to need is an augmented matrix, and we're going to need row operations and Gaussian elimination. Okay, so here we have a system of equations, and we're going to use it to create an augmented matrix, which is going to, in this case, be a 3x3 matrix next to a 3x1 matrix, all in one giant matrix. And we're going to fill in each element using only the coefficients and constants in the equation. So we had 0x, now we have 4y, 1z, and we're going to fill in the rest quickly. And now we have our augmented matrix. The goal now is to use row operations and Gaussian elimination to turn our augmented matrix into row echelon form. So here we have an example of row echelon form, and we know row operations. Let's see if we can figure out how to turn our augmented matrix into row echelon form. So take a few seconds and look this over and see if you can figure it out. Okay, time's up, so let's do it together and see what we got. First, we're going to multiply row 2 by -1. Now that we have a positive 1 in the first column, we're going to swap row 1 and row 2. Now, to get a 0 in the third row first column, we're going to multiply row 1 by -3 and add it to row 3. Now we want to turn that 4 in row 2, column 2 into a 1. So we're going to multiply row 2 by 1/4. To get a 0 in row 3, column 2, we're going to multiply row 2 by 2 and add it to row 3. And last, we need to get row 3, column 3 to be a 1. So we're going to multiply row 3 by -2/17. And our augmented matrix is now in row echelon form. We need to return this back to our system of equations, and then we're going to solve them. Well, Gaussian elimination has already shown us that z equals 0, so we can actually remove z from the system. So we have y equals 5, x plus 5 equals -10, so x is -15. But we're not done! We need to plug these answers into our original system of equations and make sure they are correct. And lo and behold, they are. And so we have our solution set of x is -15, y is 5, and z is 0. Now we're going to talk about determinants and Cramer's rule. No, not that Cramer. Determinants can be used to solve systems of equations too.
How?
I can guide you, but you must do exactly as I say.
First, how do you find the determinant? To find the determinant of a 2x2 matrix, we cross-multiply and subtract. We're going to take row 1, column 1 by row 2, column 2, and we're going to subtract row 2, column 1 times row 1, column 2. So for example, the determinant of matrix B is 5 times 3 minus 1 times 2. So now we're going to take this system of equations and use determinants and Cramer's rule to find the solution. We're going to make a 2x2 matrix for the coefficients of the variables, and we're going to leave out the solution for now. We're going to get our main determinant, which is 2 times 0 minus 3 times -1, which equals 3. To find the determinant of x, we're going to replace the x column with the answers. So we get 25 times 0 minus 3 times 10, which is -30. To find the determinant of y, we're going to replace the y column with the answers. And we get 2 times 10 minus -1 times 25, so 45. So our main determinant is 3, the determinant for x is -30, and the determinant for y is 45.
Okay. Now I'm supposed to say, that's interesting, but then you say...
But what?
But you already know what I'm going to tell you.
That's right, we're not done! To find the solution to our system, we take the determinants we found and do some basic division. So for x, we get the determinant of x over the main determinant, which is -30 over 3, so x is -10. And we're going to do the same thing for y. The determinant for y over the main determinant, which is 45 divided by 3, so y is 15. But we're still not done. We're going to plug our answers into our original equation, and everything checks out. So how do you find the determinant for a 3x3 matrix? We're going to isolate the first column, and then we're going to isolate individual elements and the corresponding rows. So we're going to isolate the first element, we're going to ignore the rest of the first row, and we're going to make a mini-matrix. We find the determinant of our mini-matrix, and we multiply it by the first element. And we're going to do the same thing for each element in the first column. We're going to add them all together, but we're going to alternate the signs of each row. So the first row is positive, the second row is negative, the third row is positive, and so on. So now that we've gone through the mini matrices and the column, and we've combined them together as positive, negative, positive, we end up with our determinant for the 3x3 matrix. Now we're going to use determinants and Cramer's rule to solve systems of trivariate linear equations. Here is our new system. So we make an augmented matrix, we pull out the matrix for the variables, we find our 3x3 determinants, 1 times 40 minus 30, minus 2 times 30, plus 3 times 18. So our main determinant is 4, and we're going to replace each variable column with the answers so we can get the determinants for each variable. We get 10 times 40 minus 30, minus 20 times 30, plus 30 times 18. So the determinant of x equals 40, and let's see if you can find the determinant for y and the determinant for z. hopefully you got that both of them had a determinant of 0. Now we do some division and find our variables are 10, 0, and 0. And we can remove y and z since they're both 0, and we get x equals 10, 2x equals 20, and 3x equals 30, so our answers check out. And that's it. It's not hard. We've covered all our objectives, and you're done.
You have some skill.
So you have the skills, and what you do with them is up to you. And even though this is a video recording, I'm going to leave it open for questions.
It's metaphorical!